Okay, I guess I don't need to share any links with you. I think everybody knows how to uh, get to YouTube and watch the videos by now. But ठीक है, I'll share the link. Okay, guys. So welcome again to our quantum mechanics class. This is like the second last week. Next week we'll have our quiz on January 6th. I think that's Wednesday, 1 week from now. And the topics will be well, everything. Okay. I mean, take it, no? It's fine, right? Everything is okay, right? And I might include one or two questions about coherent states also. Okay, so don't be afraid. And what else? Your midterm corrections, I will do those midterm corrections. I promise. Okay, is this promise? I don't know which one is promise. And I'll do them before the quiz. Okay. Then what else? Then your after that, the week after next will be the last week, right? So I plan to finish discussing angular momentum. So today I will talk about the action of angular momentum operators on quantum states. So hopefully this will make the one connection that maybe you have been missing so far. Then tomorrow I will talk about angular momentum, or maybe today itself, we'll see angular momentum for composite systems. So that will bring us to addition of angular momentum. And then I will introduce the notion of Clebsch-Gordon coefficients. And I won't go into great depth in Clebsch-Gordon coefficients, but so everybody should know are, and if needed at any point in your research, you should be able to, like, okay, go back to some text and refer and do the reading on your own, and learn what Clebsch-Gordon coefficients are when you need to, okay, in greater detail. So at least to that extent, I will cover that. Then after that, the couple of topics I think are important, which we have not covered. One is so in angular momentum only, I'll talk about spherical harmonics and solutions of Laplace's equation in spherical coordinates. And then approximation methods I have not touched at all. Those are very important. So I'll talk at least about WKB. Okay, and maybe one class for perturbation. So the goal is to cover at least whatever is considered the normal standard syllabus for introductory quantum graduate quantum mechanics. Okay.
So when will be our last class of this semester?
So last class, I mean, as per the schedule, 1 second.
14 January.
Right, as per the schedule, 14th is the last class. 15th onwards, you have the end sem exams. 15th, 16th, 18th, 19th, 20th, these are your end sem exam days. So yeah, I mean, we'll have about, let's see, 1, 2, 3, 4, 5, 6, 7, 8 more classes or something like that, which is more than enough to cover the material that I mentioned. If you are feeling that it's too much and you want me to skip some material, I can consider that also. Okay, so I'm not like I understand that you will have a lot of work to do for your end sem, so like you'll probably have some more quizzes coming up and so on. All right, so we've talked about in the past few classes, right? We've talked about angular momentum, and I've talked about right. I've talked about, so for this purpose, I've introduced the notion of a group, right? I've talked about what a group is, what is SO3. It's a group of rotations in 3 dimensions, and I've talked about the angular momentum operators, how they generate rotations, and I've talked about both the operators in the functional formalism. That means in terms of R cross P, where P is the differential operator, derivative operator, and also in terms of what do you call it? The in terms of the angular momentum operators as matrices, without any reference to any derivatives, and just considering the what do you call it, commutation relations. So we have derived the spectrum of the angular momentum operator. So today is okay. So today I'll talk about the action of angular momentum unitary operators and their action on quantum states. Okay. So this hopefully should sort of complete the logical framework of angular momentum, barring the discussion of composite system, addition of angular momenta, which I will cover afterwards. Please let me know if traffic noise is visible, is audible from the background. If it is, then I can proceed. Right. So we've talked about angular momenta in a couple of different respects, right? So I've talked about the angular momentum operators, for instance, and their eigenstates and eigenvalues, commutation relations, ladder operators, and so on, right? And the thing is that for this, you don't need any representation of the operators. You just need the commutation structure, right? Just the algebra. Just from the algebra, you can derive everything. Then I talked about groups and SO3, group theory and SO3, right? And also U1 is the same as SO2, as I've explained. Then I've talked about this thing, angular momentum as the generator of rotations, right? So when we say a generator of rotations, what does it mean? It means that the angular momentum operators generate. So what are rotations? Rotations correspond to elements of the group SO3. Right? So angular momenta will generate those elements. Now, but this angular momentum as generator of rotations I've talked about in the in the functional form, that means the action of operators on functions fx, y, z, right? So for example, an infinitesimal rotation, this y d theta, like this kind of an infinitesimal rotation. Okay? And then I showed that this operator O has to be of the form exponent minus I by h bar d theta Lz, right? For example. Okay, so now today, let me talk about spin one half systems. Now, so let's say that you have a spin one half state, right? And you know that a spin one half state is described by two complex numbers, alpha, beta, right? Before normalization. But what is this alpha and beta, right? These alpha and beta are eigenvalues of Sz, right? Or more appropriately, I should say I can write this as alpha times the up state plus beta times the down state. The up state is 1, 0, and the down state is 0, 1, let's say. And what are these states? These states are eigenstates of Sz, right? The angular momentum operator along the z direction, right? But now when I say that I have Sz, what does this mean, right? Sz is defined with respect to some lab frame, right? You have some observer. Again, the observer doesn't need, there's nothing about a conscious observer or anything, okay? This is just a observer is some apparatus which makes measurement. And this observer is in a laboratory. In the laboratory, there is some coordinate system, x, y, z, right? So it is with respect to this coordinate system that we define the operator Sz, right? When we say that Sz measures the z component of the angular momentum, it is with respect to this frame of reference in the lab. Do you understand this fact?
Yes, sir.
Right. Okay. So now one can imagine that a change of basis of the lab frame, right? So that means a change of basis in what sense? So you can either perform a translation, or what is the other option? A rotation, right? So we'll stick with rotation. So that means you change to a different set of coordinates, right? Something, let's say x prime, y prime, and z prime. Is this right? 1 second. It should be x prime, prime. You have to make sure to maintain the same handedness, right? So we have gone from this coordinate system to this coordinate system. And how do we go from this coordinate system to the other one, right? How are these two coordinate systems related? They are related by some rotation SO3 in SO3, right? Some element of SO3. So I would write for instance, vectors in my coordinate system, rotated coordinate system, let me call that O, O prime, and let me call this O. And I would say that these are given by some matrix times XYZ, right? And what is this matrix? This matrix is a element of SO3, right? So this is my rotation matrix. It's a 3 by 3 matrix. So now, please ask me if you have any questions at any point in time, okay? And if anything is not clear. Is this okay so far? Okay. So now one can ask, what happens to Sz and the state psi right? How do these transform? As we go from this, the O frame to the O prime frame, which are related to each other by rotation, your definition of S of Z will change, right? Because now S of Z has to be defined with respect to the prime Z axis. And similarly, your state psi will change to some other state psi prime. So the question is, what should be how should we transform? How should we do this, right? How should we perform this transformation? So for the state psi prime, we can imagine that there will be some operator, right? There will be some operator which relates the first reference frame and the second reference frame, right? Now, what is the relation between the two frames of reference? The relation is given by this group element, G. Let's call that G, right? So I can write it as some operator which depends on the relation between the two reference frames. That operator will be a function of G, right? Now, so this just says that the operator depends on the two reference frames, and this is a more compact way of writing the same thing. Now, what should be the form of this operator? Well, one thing is that it should be a unitary operator, right? Why unitary? Because, well, if it's not unitary, then you are changing the norm of the state, and you obviously don't want to do that, right? You want probability to be conserved, so the norm should remain a constant. And this operator should depend on the group element in some way. Whatever the group element is, right? What else? It should be a 2 by 2 matrix, right? Because my state is a two-dimensional vector, so this has to be a 2 by 2 matrix. So let me write this operator A in the following way, okay? I will explain this notation. Okay. So I'm writing it as a matrix. These are the matrix indices M and M prime. This J is equal to 1/2. Why 1/2? Because it corresponds to the angular momentum, the total angular momentum of the state. So this is also so we are talking about, we are working in the J representation of the group SO3, right? And I've told you that any group has many representations. So for instance, if you are working with SO3, you can have representations for J is equal to J can be 1/2, 1, 3/2, 2, so on, right? Corresponding to different vector spaces of dimension 2j plus 1. And 2j plus 1 is equal to 1, 3, 5, 7, and so on. Sorry, not 1. We'll start with 2, and then 3, and then 4, 5. So we are looking at the representation of J of SO3, which corresponds to J is equal to 1/2, right? And our vector space is 2-dimensional on which the group is acting. Here, in this case, when we talk about X, Y, Z, this is which representation? This is 3x3 matrix, right? So it corresponds to the 3x3 matrix. It corresponds to the J is equal to 1 representation, right? So the same group element, so the same member of the group has a representation as a 3x3 matrix, which acts on vectors, and it has a representation as a 2x2 matrix, which acts on spinors. These objects are called spinors, right? Such states, these states are called spinors. Yeah, please ask the question.
Sorry, sir.
Yeah.
Sorry, sir.
Sorry for what? Like, do you have a question? Ask the question.
No, sir. No, sir. I don't have.
Acha, you raised your hand, that's why. Okay. So I would write the corresponding matrix. So the matrix representing the group element G is written as D of J M prime J G. So for example, if I have this would be a 2x2 matrix, but for the same group element in the J is equal to 1 representation, I would have a 3x3 matrix. Right. So these two represent, physically they represent the same rotation. Okay. But one acts on spinors, the other acts on vectors. And what is this index M prime? So I can write psi, my psi I can write as alpha up plus beta down, right? Now what are up and down? As I told you earlier, up and down are eigenstates of Sz, right? So this is the eigenstate of Sz with eigenvalue +1, right? And this is an eigenstate with eigenvalue -1. So what is the state psi? The state psi is a superposition of a state. I can also write this as +1 and as m is equal to 1 plus beta m is equal to -1, like this, right? So the eigenvalue of Sz, it labels the basis vectors, right? Now when I go to S, the new frame of reference psi prime, again in psi prime my states will have a decomposition. I can write these as some up and down states. Now what are these? These are eigenstates of which operator? S of Z prime. So the operator in the in the rotated frame of reference, right? But what are the eigenvalues? The eigenvalues are the same. With eigenvalues +-1. M prime is equal to +-1. So I can write this as alpha prime, M prime is equal to 1, beta prime, M prime is equal to -1, like this. So when I write dj m prime, that is what these matrices denote. They denote the transition from the unprimed frame of reference to the prime frame of reference. And I should write this as m prime m, right? And you can think of this as +1 -1 +1 -1, where this is the m prime eigenvalue and this is the m eigenvalue. Okay. Now this is the, so we will look at explicit examples of this in a second. Okay. So what happens now? Let me write the state psi as in this way. I will write it as alpha m sum of alpha m psi m or phi m, and where the sum is over all the eigenvalues. Okay. So m is equal to +-1 in this case, right? So you can write psi prime as m prime is equal to +-1 alpha m prime phi m prime, and this is equal to dj, right? So how are these components related to these components? Vipul, is that a question or a statement?
This question, sir.
Question, right? So yeah, so what you're asking is that how can eigenvalues be written in terms of states? And I mean, every eigenvalue corresponds to an eigenstate, right?
Yes, sir. Yes, sir.
That's all I'm saying.
But
And
here
these
is the sir
eigenstates
eigenvalue is
Hmm?
plus or minus one for a state
Right.
matrix. So you can return in the form of state m equal to 1 and m equal to minus 1.
So, I mean, all I'm doing is labeling the eigenstates. These are the eigenstates, right? The plus up state and the down state. These are the
Yes, sir.
eigenstates, right?
Yes, sir.
These eigenstates are labeled by the corresponding eigenvalues.
Yes. No.
That's all
Okay.
I'm doing, right?
Yes.
I mean, again, it's I'm not doing anything very complicated, but maybe you need to think about this for a little bit just to absorb it. Okay. So these states can be written as, right? It's a matrix product now. So I can write this as dj m prime m, right? And so let me write down the expression. This alpha m prime will be equal to dj m prime m summation of over m times alpha m, like this, right? So this is just saying that this alpha prime beta prime is equal to this matrix, which is dj m prime m corresponding to some group element G. And this is a unitary matrix. Now let's look at some examples. Things become clearer with examples, right? So now I have told you that these what do you call it? Rotations are generated by your angular momentum operators, right? Now, what are the angular momentum operators for spins? For spins, that is this J is equal to 1/2 states. What are the angular momentum operators? This Sx, Sy, and Sz. These take the form of Pauli matrices, right? Right. What is this? This is equal to h bar by 2 sigma I, where sigma I is equal to xyz. Right. So you have sigma z is 1 0 0 minus 1. Sigma x is 0 1 1 0. Sigma y is 0 I minus IC. Right. I mean, this is one of the first things that we looked at the beginning of the semester, at the very beginning of the semester, when we talked about quantum mechanics, and right? I talked about states and operators, and I started with the example of the spin half system, right? So we are coming back to that. And these are my angular momentum operators. So what I'm saying is that this group element, this representation of the group element G will be generated by these operators S of I, right? And so how is the generator related to the thing it generates? It is related in how do you generate a group element from the generator? By now, maybe you should know the general procedure. Anybody? I take something which is my generator. What do I do with it to get the corresponding group element?
Exponential.
Exponential, thank you. Minus I by h bar, right? So if I talk about a rotation around the z-axis, for instance, I will say exponential minus I by h bar, then my angle theta, and then the operator of z. Okay. This will give me the corresponding representation of the group element corresponding to the rotation around the z-axis by theta. But it will give me a 2 by 2 matrix, something which can act on spin. Right? So again, let us go back and look at the whole thing logically, right? What are we doing? We are performing a change of basis in our lab. When we perform a change of basis in the lab, all the vectors will transform accordingly. But all of the states that I have and all of the operators that I have, they will also have to transform. Right? So you should think of these states as just like coordinates, just like you think of a vector, just like you think of a vector in a certain frame of reference. You should think of the state also as a vector only. I mean, it is a vector, right? But it depends on the frame of reference of the observer. Now, these three-dimensional vectors will transform according to these SO3 elements, which you know the explicit form of, right? You have looked at examples with like 1 cosine theta, sine theta, minus sine cosine, right? As an example for rotation around the z-axis or the x-axis. Right? Now, I'm just explaining to you, well, how do you construct the same thing for the spin 1/2 state? You didn't know how to do that, right? We didn't know how to do that till now. So how do we do it? We do it using this notion of group representations. So you have the same group element, which represents the same physical rotation, but it has two forms. One is a 3 by 3 matrix and one is a 2 by 2 matrix. This acts on 3D vectors, right? This acts on 2D vectors, or also known as spinors. And these states, these rotations are generated by some generators. Those generators will also be either 2 by 2 matrices or 3 by 3 matrices. By the way, do you guys have some class coming up at 9 o'clock?
No, sir.
No? Okay, then I guess people are just finding this angular momentum thing very difficult because I'm seeing people leave. So, I mean, angular momentum isn't the easiest topic, but I'm doing all I can to make it as simple to understand. Okay, so now how do I generate the corresponding group element? Okay, let me look at that. So okay, so this is how the state transforms. The state transforms according to this action of this group. How does the operator transform? I have told you that operators will also transform, right? So if you have some operator U defined with respect to the first reference frame, then this will transform to some operator U prime with respect to the rotated reference frame. How should this operator transform? Now the state transforms according to this rule. this unitary operator, which is the group representation matrix. So how should the operator U transform? Any ideas? This is something that you have done before in the homework and also in one of the quizzes or the midterms. Any suggestions? If the state corresponds according to the matrix, how does the operator transform? Anybody? Vipul?
Sorry, U dagger.
Say that again.
U dagger, sir.
No, U is the operator I want to transform. Okay, U is some operator that I want to transform to U prime. Right? And the transformation operator is given by this AG. AG is the transformation matrix. In the exam and all, you might have seen a different notation. I would have written this AG as U. Maybe that's why you're thinking of it like that. So let me write it like this. Psi prime is equal to some operator U times psi, and and then I have some operator S. How does the operator S transform? How do you get S prime from S?
So U dagger U inverse. Okay.
What is it?
U dagger S prime S U dagger S U inverse.
Thank you. Right. The operator transforms in this way. Why is this? Because so that when I look at the action of the transformed operator on the transformed state, what do I get? This is the transformed operator. This is the transformed state. So this cancels out, and I'm left with one copy of U acting on S of psi, which makes sense because so if psi prime goes to U acting on psi, then S prime acting on psi prime should go to U acting on S psi. Okay. So here I would write AG U AG inverse. Okay, just a change in notation, that's all. Okay, so now let's try and calculate what these operators are for the simple case that we have a rotation around the z-axis by some amount theta. So what do we want to do? We want to calculate this exponential minus I by h bar theta times sz. Okay. Now again, this is a calculation we have done before, but you need to, let's do it again, right? This is the first term. The second term will be the square of that, so you'll get minus theta square sz square by h bar square. Then you will get plus I theta cubed h bar cubed sz cubed, right? And then you get plus theta 4 by h4 sz 4, and then the rest of the terms will repeat. right? You'll get SZ5 and SZ6, but SZ has the property, right? What is SZ? H bar by 2 sigma Z, right? And since we are looking at SZ by H bar, that is just sigma Z. So we are just looking at sigma Z. And sigma Z has the property that sigma Z square is equal to what? What is sigma Z square? Identity. So sigma Z cube is equal to sigma Z, and sigma Z4 is all equal to, again, identity. So this term is sigma Z, this term is identity, this term is sigma Z, again sigma Z, and this term is identity, right? And you can see that you have complex term, real term, right? So you can collect all the real components in this way. 1 minus theta squared, right? Sz squared is the identity. So don't forget to write the identity so that you know that it's a matrix. And also there'll be a factor of 2 factorial, 3 factorial, and 4 factorial, which I put by 2 factorial. Then theta 4 by 4 factorial identity. These are all the real parts. And then you have the complex parts. So the complex parts I can write as minus I, right? Minus I. And now in each of the complex parts, I have sigma Z common. So I'll take that sigma Z out, right? And then I get 1 minus, sorry, not 1, theta minus theta cube by 3 factorial plus theta 5 by 5 factorial and so on, right? You have all done this calculation, I hope. I've given it so many times, so I hope that you have done it. So what will this give you? This will give you cosine theta, right? Cosine theta multiplied by the identity matrix. So we will get 0, 0, cosine theta, cosine theta. And this will give you minus I sigma Z times sine theta, right? So sigma Z is 1 minus 1. So we'll get sine theta 0, 0 minus sine theta, right? Now I'm making some mistake somewhere. I don't know what mistake I'm making. Let me just make sure. Just fix that. What is the mistake? No, it's fine. It's fine. I think it's fine. So what does this give us? This gives us the matrix cosine theta minus I sine theta, 0, 0, cosine theta plus I sine theta. So exponent of minus I by h bar theta s of z. So what is this? This corresponds to the matrix for j is equal to 1/2 m prime m for the group element which corresponds to so I'll just write it in words, rotation by theta around z axis. And I can write this as, so I'll write that as d 1/2 m prime m r z theta, right? Rotation by theta around z axis And what is the matrix? It is e to the minus I theta 0, 0, e to the I theta. This is the matrix which I will, this is how states will transform under the rotation. Now this matrix looks different from what you expect for three vectors, for three-dimensional vectors. For three-dimensional vectors, remember, what do you get for three-dimensional vectors? So if I have D1 m prime m for the same, this thing, this is a rotation around, I will get cosine theta minus sine theta, cosine theta, 0, 0, 0, 0, 1, right? And what am I getting here for 1/2? I am getting e to the I theta 0, 0, e to the, sorry, minus I theta. Right now, these two matrices look very different, but this is what is happening when I act on, right? I get two different expressions, and I'm missing a factor of 1/2, right? That's very important. This factor of 1/2 is very important, and I missed that. You see this factor of 1/2 in the definition of S of Z, right? S of Z is h bar by 2 sigma Z, right? So this factor of 1/2 I've forgotten everywhere. So let me put this factor in. What will happen? I will get, I'll get theta by 4, then 2 to the 4th power. Basically, theta will be divided by 2 everywhere, right? So this will become cosine theta by 2, and this will become sine theta by 2. This is very important. I should not have, well, theta by 2. Again, same thing here, theta by 2. I'm putting it in red just to emphasize how important it is. Okay. So now let's look at what happens to a state. So I have alpha beta. What happens to alpha beta? It becomes alpha prime beta prime, which is where alpha prime is equal to e to the minus I theta by 2 alpha, and this is e to the I theta by 2 times beta. This is how my state changes as I go from the one, O to O prime. So what is O and O prime again? Let's say this is O, and what is O prime? O prime is exactly the same state, but now I have rotated around the Z axis. I have rotated around the Z axis by some angle theta. So this is O prime. Okay. And so how does the state change? The state changes in this way. Now there is a very nice consequence of this fact, that let's say let theta is equal to 2 pi. Right? So what is theta equal to 2 pi? This corresponds to a complete rotation around the Z axis. Right? So under this rotation, what will happen to vectors? Under the rotation by theta, what will happen to XYZ? XYZ will go to, what will happen to it?
Same XYZ.
It will remain XYZ. Right? Because you are just returning the axis back to the original configuration. But what happens to the vector psi under the same rotation? It goes to e to the minus I theta by 2. So you get e to the minus I pi 0, 0 e to the I pi times alpha beta. What is e to the I pi?
-1.
So under a 2 pi rotation, the state psi goes to the state minus psi. This is the fundamental, one of the fundamental properties of spin, of spinners, spin 1/2 particles like electrons. That if you rotate the particle by 180 degrees, or what happens is that you don't get the same state, you get negative of the state.
-360 no, sir?
2 pi is, yes, 360 degrees. Thank you. 360 degrees. And so if you want to return to the same state, you have to perform a 4 pi rotation. Right? And this is, so that's why these objects are called fermions. Because another way to think about this rotation is that, let's say you take 2 spins and you interchange them. That interchange corresponds to a rotation by 2 pi, right? I think so. Get confused sometimes. So I hope that you can do these calculations. So I'll give you your next whichever homework number XX. I don't know which one it is. Okay.
7.
Calculate, huh?
7, sir.
अब पता नहीं भैया क्या है 7 है 6 है 7.1 लेंगे. So calculate this these matrices for Rx call it alpha and Ry beta. Okay. So for rotations around the x-axis by an angle alpha and rotations for a y-axis around y-axis by angle beta. So I have shown you that the matrix for Rz theta is e to the minus I theta by 2, 0, 0 e to the I theta by 2. So I want you to calculate the respective matrices for these two. Okay. And what else? Right. And then I can continue with the same thing, and I can ask how does the operator change in the new coordinate system? So I have S of Z prime. S of Z prime will become, this is my matrix, right? This is my transformation matrix. So I will just write this transformation matrix as A of G, just to. So it will become A of G, SZ, A of G inverse. Now A of G is e to the minus I theta by 2, 0, 0 e to the I theta by 2. So A of G inverse, this is a unitary matrix. So the complex conjugate transpose is the inverse. And you can just look at the matrix and read off what the inverse is, right? So what is S of Z prime? S of Z prime becomes minus theta by 2, 0, 0, minus, plus theta by 2. S of Z, what is S of Z? It's h bar by 2 sigma Z times theta by 2, 0. Right? So what do you get? You get well, you can work it out. It remains S of Z. So under these rotations, under a rotation around the Z axis by an angle theta, S of Z remains invariant, right? Which makes sense. Because what does S of Z do? S of Z measures the angular momentum around the Z axis. So if the Z axis remains unchanged, S of Z will remain unchanged. But S of X will not be equal to S of Y, and S of prime will not be equal to S of Y. Okay. So this is how you connect rotations to the quantum states. Okay. And remember that you have similar generators, like you have these Pauli matrices Sx, Sy, and Sz. We have calculated those generators for the three-dimensional representation also, right? Jx, Jy, and Jz. So if you remember, Jx had this form 0, 0, 0, 0, 0, minus 1, 1, 0, etc. Right? So I'll stop here. And again, tomorrow I will look at a concrete example, which is that of spin precession in a magnetic field. And then after that, we will talk about addition of angular momentum. Okay. So I'll leave it there for today. Questions? Any questions? No questions?
So how 2 pi rotations corresponds to a phase change of -1? So pi. So if upstate is rotated by pi angle, we have downstate, right?
Upstate is rotated by pi angle. We have downstate. How do you say that? See, what you are thinking of is that you're thinking of this vector and you rotate it like this, you get down. This is what you're thinking of, right?
Yes, sir.
Right. But these states are not three-dimensional vectors.
Okay.
Right? These up and down states, they are not three-dimensional vectors. Right? So we say up and down, but up and down does not literally mean the vector up and the vector down. Right? What is up and down represents the fact that if you take the Z angular momentum of the up state, you get plus 1/2 plus h bar by 2. And if you take the Z angular momentum of the other state, you get minus h bar by 2. Right? So in one case, you get angular momentum pointing in the positive z direction. In the other case, you get angular momentum pointing in the negative z direction. So that's why we call this the up state and this the down state, right? But it's completely incorrect to think of the up state as the vector z and this as a vector minus z, right? These are not three-dimensional vectors; they're two-dimensional vectors. Right? And this is one of the reasons why, I mean, when we first study angular momentum of spin 1/2 particles, especially, it is a little difficult to absorb because it goes against our intuition in many ways. Right? For example, our intuition says that if you take some system and you rotate it around by 360 degrees, you come back to the same system, right? But for a spin 1/2 particle, you are not coming back. You are picking up a phase of -1, and this is not something that happens with classical particles, right? And so spin 1/2 particles are not classical, and we don't have spin 1/2 particles like around us. Like they are generally what happens is that what we end up observing is some combination of spin 1/2 particles which adds up into something that is spin 1, like this pen, right? So this pen doesn't have half integer spin. If I look at the angular momentum of this pen, it will have integer spin, and when it rotates around, I get the same thing back. Okay, so this is very important to understand this point, that when I say spin up, when I say the up state and the down state, I mean in the context of the angular momentum value. Is this any clearer to you, Sol? I don't know.
Yes, sir.
you have to like work out these calculations for yourself, and if you do that, then it will start to, well, I don't know if it will start to make sense, but at least the technical aspects you will start to understand better. Okay. So this is actually angular momentum used to be one of the weakest topics for me when I first studied quantum mechanics in undergraduate and in graduate school. I sort of skipped over angular momentum. I was always very scared of angular momentum, right? And you can see why. And but then later on, what happened is that when I started doing research, angular momentum became the most important thing for me to understand, right? And so I had no choice. I had to go and understand it better. So it is a little complicated, little abstract than some of the other topics we have looked at, but everything in physics cannot be boiled down just to the very simple things. Some of the concepts are not so simple. That's why you guys are doing MSc, right? Otherwise anybody will do MSc, right? That's why your degree has some value. At least I think it has value. I don't know what about anybody. Okay, so I'll stop the recording.